All right, thanks, Jimmy, and thank you for having me here. All right, so I'm Jeffrey Gao. I'm currently a PhD candidate at Caltech. I'm working in an AI lab here in Caltech, and I mostly focus on medical applications. Um, so basically, today I will share our work of integrating AI into heart ultrasound. And it's the entire pipeline from the motivation, the research phase, the model training, all the way to the real world application deployment. And these are all aimed at making heart ultrasound as accessible as checking your blood pressure. Here is the talk outline. So here's how we'll go through it. First, I will share some background why the heart ultrasound today needs AI, and then I'll share two projects of our labs. First is the right atrial pressure estimation project. It turned out to be a real-time application, a iOS application built from scratch to run on iPads. And the second project is ejection fraction estimation from PLAX view, so the Parasternal lung access view. And that's kind of something traditionally not done, and we have done it for a reason, which I'll cover shortly. And finally, I will share our where we'll see this thing going. So our vision is toward a routine and AI-powered heart assessment. All right, let's first start with the background, the why. So why heart ultrasound today really needs AI? Um, yeah, before I cut to AI, I'll first share some facts we are facing today. We are really having a huge burden toward treating heart failure. It affects over 6 million people in US alone and 10 million in Europe. It is the leading cause of hospitalization in the US, and it's also the number one cause of death in the US. And it's incredibly expensive. We spend, 30 billion per year in the US alone for just for treating diseases. And the frustrating thing really is the heart failure is often manageable. The heart conditions is manageable if caught early. The bottleneck really is timely diagnosis. Nowadays, most people just don't get heart ultrasound or their heart checked routinely. And it's mainly because of the cost is just too high, both money-wise and time-wise. You'll um like if you want to take a heart ultrasound, you will first need a session for referral and then an appointment with a sonographer to take an ultrasound video. And after that, you can finally have a session with your cardiologist to maybe together review that video and see how it goes. And the chances are that most people just don't get that done, don't get that checked routinely. And the chances are that when someone finally gets their heart scanned, severe symptoms has already taken place and they're already in an emergency room or ICU. And secondly, even in top hospitals, delay happens, especially with like a busy ICU or ER. The reason is the same. Basically, the expert resources are limited. We need a sonographer, we need a cardiologist to be available in order to take the scan and interpret the scan. Yeah, and we also need the large, expensive ultrasound card to do it. And that's for top hospitals. Now imagine how like rural clinics or urgent care settings, most of them don't even have an echo machine. So what we are missing is the chance to intervene early. Uh, Let me be clear about one thing. So this is not a hardware problem. This is, uh, the portable handheld probes for hard ultrasound scans exist. The bottleneck here really is the workflow. So the sonographer and cardiologist who can scan and who can interpret. And as I mentioned, the missed prevention and delay in emergency settings really cost lives. The treatable conditions become emergencies, you will miss that precious early intervention window. The patient might have only had some mild fluid buildup, which is very treatable with some simple oral medicines. But by the time when they are finally getting scanned, when they are in the emergency room, they'll be needing some IV diuretics or hospitalization. And that's basically our research motivation. So we want to build tools um to make the scanning easier and faster. And we also want to make the diagnosis process more accessible and automated. Here's our research overview. We basically have two AI models. One model for the image acquisition guidance, and this can help a non-expert get the right ultrasound view and replace the need of rare, rare resourced skilled sonographers. And the other model is for heart status assessment for the interpretation. This model will estimate key heart metrics from that view from the first model, and this will be done automatically. And we've made the models lightweight enough to run locally with a handheld device. So you don't really need all the iCloud, the Wi-Fi, or the GPU servers. Just a probe and a iPad or a phone will work. Yeah, that's kind of a high level um, overview of our research. All right, let's dive into the detailed projects. Our first clinical application is right atrial pressure estimation. Um, the right atrial pressure is often used to measure a key complication, volume overload. So I'll talk about volume overload for a second and then get back to right atrial pressure. So volume overload, VO, it is a frequent complication of a vacant heart with a patient whose heart is not that healthy. And volume overload is often preventable. If caught early, it will be easily managed with oral medication. But as I mentioned, most patients only get diagnosed when they starting to feel some symptoms, maybe short of breath, maybe some organ failure already, and they ended up in the emergency room and finally get a scan done. And even if the patients are taking the initiative, they want to monitor themselves at home, all they can do today is to self-monitor their weight change or blood pressure change, which I would say really is not reliable at all. And if they want some more serious monitoring happen, the true volume status assessment requires an echo. And that take days. And as I mentioned, right atrial pressure or RAP is the indicator, the thing we want to measure for volume overload. We can infer from the behavior of the inferior vena cava, the IVC area, and the process is very well established. It's the clinical standard. But, performing the process quickly and accurately is not the standard. So our goal really was to automate this process to first locate and identify the correct IVC view, and second, access the right atrial pressure value from that video clip. And we hoped we can do it all in real time on device. And that's what we have done. And in order to build a reliable model, of course, a massive and diverse dataset is needed. So we've built this largest dataset ever used for volume status classification. It consists of 16,000 labeled examples, and it's across patients aged from 18 to 102 years old, using 4 different models, using 4 different probe types, and it's with 45 different cardiologists providing measurements. So this kind of skill really gives us the robustness and the model, and this will help our model to generalize. And based on this data set, we trained 2 models. The first one is the IVC view classification, and second one is a volume status assessment model. The first one is based on the X3D structure. It's a transformer structure, and the second one is based on slow fast. It's a ResNet. It's a convolutional network structure. And the results were very encouraging. We've got 96% accuracy in classifying the correct IVC view. And as for our second model, the rough predictions really matched the expert cardiologist against invasive measurements, which are the heart catheterization, and it's the gold standard. And importantly, the model also hold up when tested on an external dataset from the University of Montreal. So this means this wasn't just fit into one dataset, a model really generalized. And this work has been published in Journal of the American College of Cardiology Advances. And yeah, but building a model isn't enough. The model has to be usable. So we have integrated the models into an iOS app. And yeah, basically by doing that, we allowed the possibility to take a probe while collaborating with Butterfly. So we used the Butterfly IQ probe and connecting that probe onto an iPad, and that's all we need. So an iPad, maybe $1,000, and a Butterfly probe, a few thousand, around 4,000 or $5,000, and that's all we need. And along the way, there are some technical details we encountered. I've listed some of them. So we first used PoML system by Apple to deploy our model onto the iOS system. And we handled the dynamic scaling using still Apple's metal performance shaders framework, so we are able to use GPUs from iPads to do the pre-processing steps. And we've created a robust data stream handler using a double dictionary lock to ensure, so this purpose is to ensure, like, as streams incoming, as real-time data incoming fast, to ensure the efficiency and the strict sequential order to handle them. And finally, we manually mapped cross-plat. We did some manually mapping. So basically, that is to ensure the cross-platform consistency. And that's because we really cannot use all the Python package on an iPad. They just don't have those package. So we basically implemented some of the package by manually. And in the end, we have this real-time right atrial estimation application running entirely on an iPad. Here is a small demo video of ours. All right, so that's my, I would say that's me scanning on myself. So see how, like, when it detected the IVC area, everything turned green, and we have this green circle showing where the IVC is. And as we move from it, everything turns green and red. And once we get a stable enough IVC view, we will be initiating a sniff scan, which is a sniff or a deep breath. And after a sniff scan is conducted, we will have a real-time result, a real-time estimation for the patient's right atrial pressure. So yeah, that's basically our first project. All right, I'll move on to the second one. The second project is ejection fraction from PLAX view. So first, I will share a little background about what ejection fraction is. Ejection fraction, EF, tells you how much blood the left ventricle pumps out. So basically, how strong your heart is. And it's critical for diagnosing heart failure. It is clinically assessed with apical echo waves. And most current AI tools really focus on apical four-chamber views to give an estimate, like EchoNet dynamic. It's a strong work researched by a Stanford team, and they did well. But we wanted to explore a different view, which is a PLAX view, the Parasternal lung axis view. And there's a reason for that. Why do we choose PLAX for EF? The first and most important reason is that the PLAX view is easier and more stable to acquire. This is especially important for our goals. We are aiming for those inexperienced operators to scan themselves. So as you can see from the images here, the traditional view, the apical four-chamber A4C view, is scanned from bottom side up, so from a little near to your belly area and toward your heart area. So it really would be harder to be acquired by those obese people or elderly patients where they have fat accumulating in those areas, especially with a small handheld point of care probe. That would be hard. PLAX view on the other hand is, top side down. It's from your neck area towards the heart. That really is easier and makes a scans more accessible. So we really want like the potential users of our research to be like either they will be inexperienced for sure, and I want them to be really um, get the scans easier rather than tougher. We are not aiming for those experienced sonographers to take a echo scan with a handheld device. And the PLAX view is already a part of the routine echo exams, so it really is widely available. And but the PLAX view is not routinely used for EF estimations because first, there's no large data sets existing now, and there's no research about, there's not any research publishing any validated models about estimating ejection fraction from PLAX views. And the PLAX view it only shows part, although a majority part of the left ventricle of your heart. But in clinical standard, doctors tend to be hard to predict only from a partial view. So I think that's the kind of the biggest obstacle why doctors nowadays is not using PLAX to estimate ejection fraction. But machine learning or AI models are different. They can figure and find all those minimal and small details in the heart. The majority part of heart is well enough for AI model theoretically to predict the ejection fraction, and that's our motivation. And it turned out to be very doable and we achieved good results. And still, I'm gonna first start with the dataset curation, which is basically the most important thing for training any type of machine learning model. So, like the first project, we'll need two models. One for classifying the correct view, in this case, the PLAX view, and the second to estimate a ejection fraction value from that view or video clip. Here is a process how we created this data set. And this really is the first public large-scale PLAX dataset with merged EF ground truth values. So we've used three public available datasets to build the video classifier. The first one is the EchoNet dynamic dataset, the dataset from the Stanford team. In that dataset, we have 10,000 A4C videos, the apical fold chamber view videos, and those videos are with EF, with ejection fraction labels. And the second dataset we used is called EchoNet LVH dataset. It's another Stanford generated dataset. It consists of 12,000 PLAX views, but unfortunately, those views are without EF labels, so we cannot just take the dataset and train a model. The third dataset is mimicked for echo dataset. It's a big and popular dataset in medical imaging, and we extracted 14,000 other videos, which basically is all the other video, or maybe some random ultrasound clips other than the A4C and PLAX views. And with those three datasets, we are able to train this video view classifier, and this classifier is based on the X3D structure. It's a transformer structure. And secondly, secondly is the training process for our ejection fraction model. So in this pipeline, we still used the EchoNet dynamic dataset to use their A4C videos and EF labels with like correlating to the videos to train a A4C EF model. So this model basically predicts ejection fraction based on A4C video clips. And we used the Mimic4 echo dataset. We combined this dataset with our video view classifier to classify the views from the Mimic4 echo dataset. Yeah, one thing about this Mimic dataset is that most of the data in it is not labeled. So both the view types and the EF labels are missing. So we basically first used our trained video classifier to give view labels to the videos inside the Mimic dataset. And we used that to generate around 5,000 studies with at least one A4C view video and one PLAX view video. And yeah, since EF value in a study should be the same, we are able to use the A4C EF model to generate proxy labels for each study and apply those labels to the PAX videos inside the study. And with that approach, we are able to generate around 25,000 PLAX videos with EF proxy labels from A4C views. And with that curated dataset, we are able to train a model from that. So the performance is like this. We achieved a test MAE, the mean absolute error of 6.86%, which matches the apical-based tools like EchoNet Dynamic. And this really is the first reproducible PLAX benchmark. And our model outperformed all prior published results in literature. So previously we have a study. It's not really machine learning though. The GoCo study, they did use a machine learning structure, but their machine learning model is to mention the diameters and the structure parameters from the PLAX view, and they used a very complex mathematical formula to calculate a ejection fraction value, and their performance is not accurate enough. And the second study is called XOAI. They achieved a good error, like a 7.29%, but they didn't disclose any algorithm details, and they didn't publish their models. So yeah, this really is the first public PLAX EF model in literature, and our work is accepted for the MIDL oral presentation this year, which will be hosted in Salt Lake City. And that wraps our second project. All right, and our second project is still ongoing, so we will integrate these models into our iOS application sometime. All right, and let me wrap up by sharing we see this going. Our vision is really to democratize hard ultrasound scanning. we believe that real-time AI tools can bring heart ultrasound into routine care, not just hospitals, but clinics, also maybe ambulances, even homes. Anyone should be able to pick up a probe, follow some simple guidance, and get a reliable heart assessment, both real-time and instantly. Just like we check our blood pressure or glucose today, we think heart function checks should be available and become routine, and AI makes that possible. And we are actually currently collaborating with two major hospitals. We are first collaborating closely with physicians at UCSF, the University of California, San Francisco, and we are also working with a major heart hospital that has one of the most extensive, well-labeled echocardiography dataset in the United States. And we are also working with a big international company to, explore some potential opportunities. And our goal is to translate this research into real-world clinical impact. And we are really actively exploring pathways to bring these tools into industry through potential partnerships, maybe some pilot deployments, and things beyond. All right, I think that's all. Thanks for listening, and feel free to reach out by email, LinkedIn, or schedule a 30-minute with me using Calendly.